Massive amounts of raw, unstructured data systematically transforms into a highly rigid, controlled system through the intensive computational training process. Many large language models labeled as open source are miscategorized. In a professional context, this distinction is critical to understanding how the software actually functions. Open source and open weight are distinct concepts. An open weight model provides the public with the trained numerical parameters, but the foundation of the model remains hidden. In an open weight release, the provider typically withholds the full training dataset and the original build infrastructure. You are receiving the finished product, not the factory that made it. These models do not store human sentences or pre-written facts. There is no internal database or memory bank of knowledge to query. Downloading an Open Weight LLM provides a massive compressed structural file of numbers. This file is the mathematical residue of the training process. The fundamental unit of the structure is the weight. A weight is a single numerical value. Deep inside a single cell, the weight acts as a multiplier. It controls the strength of an internal signal as it passes from one layer to another. During training, every incorrect token prediction forces a tiny mathematical adjustment to the weights. This error correction shapes the model's behavior one number at a time. This micro-adjustment occurs millions of times across billions of parameters. The result is a highly compressed pattern recognition system. The final weight file is the frozen representation of the model's learned behavior, isolated from its original training environment. Using this frozen file requires an inference engine to execute the mathematical operations. When a user enters a prompt, a tokenizer fractures the text into discrete pieces. These pieces are converted into numerical IDs, so the mathematical engine can process them. The runtime environment loads the static weight file into active memory to prepare for the incoming tokens. As numerical IDs pass through the model's layers, the internal representations transform. The trained weights dictate the path and intensity of every signal. The final layer emits a spectrum of probabilities for what the next token should be. A decoding method selects the highest probability token and adds it to the sequence. Then the entire loop restarts. Inference is a mathematical process. The engine relentlessly predicts the next token based on the prompt, the context, and the learned weight structure. Integrating a closed API is convenient, but hosting an open weight model provides the engineer with physical custody of the logic. Closed APIs are governed by the provider. They control the infrastructure, the rate limits, and the safety filters. Open weight models allow for local execution on private servers. This architecture allows internal workflows to process sensitive data without broadcasting it to external corporate APIs. Builders sacrifice immediate convenience to secure total operational control over the inference process. Builders manage open weight systems by constructing distinct layers of control around the weight file. The prompt is the innermost control. It shapes temporary behavior within the context window while the underlying weights remain unchanged. Retrieval Augmented Generation, or RAG, inserts external knowledge into the prompt. This provides the model with fresh domain data without the need for retraining. Fine-tuning permanently modifies the weights. This process enforces specific styles or domain expertise by continuing the training process on a specialized dataset. Fine-tuning carries technical risks. Poor training data can damage the model's logic and lead to confident hallucinations. External guardrails and application logic form the final layer. This software architecture governs the model's actions and validates its output. Designing a robust, restrictive architecture surrounding the model ensures it remains useful and predictable in a production environment. Open weight access is not a grant of unlimited rights. Builders must navigate complex legal parameters, including commercial restrictions, attribution mandates, and specific limits on the redistribution of fine-tuned versions. Hosting these models requires significant resources. The builder is responsible for GPU hardware, latency tracking, and monitoring for model degradation. Privacy depends on the implementation of secure access controls and encryption policies. Simply owning the weights does not secure the data. Taking custody of a model's weights means accepting total operational responsibility for the runtime environment. In scientific discovery systems, error is unacceptable. Inside a discovery intelligence platform, the LLM is restricted to a strictly bounded role. It extracts structured evidence, summarizes candidate papers, and routes tasks to specialized systems. The language model must never invent facts, replace raw evidence, or directly alter scientific truth records. The scientific core is governed by exact measurements, rigid schemas, and validation logic. A validation gate intercepts the model's output. It checks every claim against physical constraints and citations before the data is trusted. The LLM serves as a language interface and an orchestration engine, but it holds no final authority over scientific reality. An open weight model provides a powerful token prediction engine. For serious scientific discovery, truth and safety exist in the rigid architectural controls built around that engine.